gone to the full scale, but what I want to make very much as my next big project is this. So this is a 2-layer geodesic sphere. You've probably seen geodesic spheres that have one layer. They're very common. You take sort of like icosahedron, you divide the triangles into sub-triangles. There are some that are 2 layers, the Expo 67 Dome in Montreal, for example. If you have 2 layers, an inner one and an outer one, it becomes enormously stronger, okay? So if you apply a local force to a big flat thing, it'll buckle. But if it's 2 layers, it's a truss structure, and so this is basically the structure that you find inside the roofs of big open spans of malls or convention centers, whatever. But if you curve that around a geodesic sphere, then it requires pentagons and this interesting structure. No one's ever made before this one you're looking at a chiral one. So chiral means it's different from its mirror image. It's like a left hand and a right hand, as opposed to being the same as when seen in a mirror. I just happen to like the chirality. If you look at this picture on the bottom right, I don't know how well you can see this, but I made a green dot on the 5-fold vertices. So if you're a geodesic dome fan, whenever you see a geodesic dome, you should look for the 5-fold points. Everything else will be sort of 6-way, and there'll be certain 5-fold points that are basically the landscape landmarks to work from. And here, if you start at any one and walk along 1, 2, 3 hops, and then turn right and go 1 more hop, you come to another. So you go 1, 2, 3, and turn right 1. And that works from any 5-fold to any other 5-fold. This is based on something called a Goldberg polyhedron. It's been around a long time. It's well known to mathematicians, but no one's ever made a large 2-layer geodesic sphere of this sort. Anyway, all I need are connectors of the sort I showed here that have all the right different crazy angles for each of these points. But that's very easy to make in software. The software that I use to create this file, this is made on a selective laser sintering machine that's about 6 inches in diameter. But that same software has already worked out the angles. I just have to turn it into little tubes and holes and be able to make those connectors. So that's the big project that I'm sort of working towards. And then again, to build it in this technology where I have little plastic connectors for the difficult angle parts, and some sort of, these are just bamboo shish kebab skewers for the connectors at a penny a piece. I can make a very large structure that I think will be really cool and nice. So that's, I'm hoping to be my big sculpture for next month. Here's one of the first things I made. It's an Apollonian gasket. It's sort of a circle, then you remove 3 big circles, and then you remove the next biggest circles you can, and you keep doing that. You're always removing the largest circle you can. Actually, my daughter was over for dinner one night, and we saw this cupcake, and said, what can we make? And he said, oh, let's make this. Let's turn the circles into hemispheres and build one. Anyway, so that came out very nicely for what that is. And it's cool as a mathematical thing. I think of it as possibly a cookie cutter mold or something of that sort. I don't know quite what to do with it. This is a pair of rhombic trichontahedra. This is one of my favorite polyhedra. This is sort of the one that I have my tombstone carved in. That's sort of how I measure polyhedra. So here you can see it. Again, I have a smaller one inside a larger one. I didn't know if this would come out. I was surprised at how well it did. Actually, you can see it better if I do that. It needs a little more cleaning up, but basically with the X-Acto knife, it ends up having the form I want. And it just suggests that there's lots more things in this family that I can go in that direction. I should mention I write a column for Make Online called Math Mondays. So every Monday there's a column of something cool you can make that's mathematical. You can go Google that and find some cool ones. One of the first ones that I did was how to slice a bagel into 2 congruent pieces that are linked together. I don't know if you've seen this, but here's a bagel. And if you gave me an actual bagel and a knife, I could do this in front of you in 10 seconds. And you cut it in half, and the 2 halves are linked like a chain. And it's kind of a fun thing to do. I recommend you do this for breakfast tomorrow. So you can easily make this on a printing machine.
Do you get more cream cheese on that?
You get more cream cheese, yes. Thank you for that question. So, how much more cream cheese do you get? This is the math assignment. If you were a group of math students, I would assign you this for homework. But it's very easy to calculate, not very easy, but it's straightforward to calculate how much extra surface area there is on this compared to your standard slice. So here's another item that was in one of the Math Monday columns. It's a friend of mine, Chaim Goodman Strauss, made this thing called a Hilbert curve out of plumbing things. It's a cool thing to make because everyone has computer models of Hilda Curtis, but you know, he's got a real one. So you can take a computer model of it and you can build it. And again, I wasn't expecting much. This was really, I was thinking this would be sort of the version that doesn't work, and then I'd have to figure out a way to make a version that does work. But it worked. There was a little slip in the x-axis somewhere up along the line, so it's a little bit off, but after you clean it up, there's overhangs, and you can see, say over here, where it started to build the overhang in the air as it got up to this Z layer, it just kind of drooled a little bit, but that drool hung around, and then it became a platform, and within 4 or 5 layers, it was building just fine, because it had something to work on top of. Then you clean it up with an X-Acto knife, and it worked out well. So again, I'm very happy with these experiments. This was another Math Monday column. This particular item we're looking at is in a museum in Germany from the 1400s, and no one quite knew what it was for a while. And it's made of all these interlocking parts, one to the next, in a ring, and it kind of twists. It's kind of a twisted torus, and it's sort of a puzzle to understand how they made it and why they made it. But you can build it out of these parts, so I just made a model of those parts. And there I am wearing it, courtesy of the MakerBot people. I didn't bring that with me, but it's a really nice thing to make because it has just identical parts. You have to snap them together. This was at the Maker Fair, the New York Hall of Science a couple of months ago. So here's a more recent experiment, and something of a failure, so I'm happy to admit the failures. This is a concept for a puzzle. There's 6 sticks, and they interlock each other, and the idea is that then they would snap together and hold themselves in place. I made the sticks, and they do fit together. It fits together very nicely. Here's actually a photo of it. But you see it needs the rubber bands. If I take off the rubber bands, then it falls apart. So it doesn't lock together. I can glue it together. It's actually sort of a nice sculptural object in a way. But I was hoping to make a puzzle that would actually click together, that each piece would be held in place by its neighbors and not be able to fall apart. But then I designed a more complex one. And this one really does work. So this has 12 sticks. There's a particular geometric arrangement to them, and they're scalloped. I think I have a picture here. So you can see how each one contacts 6 other neighbors, and it has 3 little scallops that are subtracted out of it, so that when it touches 3 of those neighbors, it's missing a part, and the other 3 that touch it, they're the missing the part, so that it all locks together. And as you put these things together, it's all falling apart. But after you snap the last one in, it snaps into place, and it's completely rigid. I have rubber bands on this now just so it doesn't fall apart in my bag. If you squeeze it hard, it'll fall apart. But it holds itself together beautifully as a puzzle. So I see this as kind of a puzzle concept that would be fun to produce in some larger quantity. This and all my other files, I'm happy to put up on the website. These are some different views of the same object. I think I'm going to conclude.
And we'll put those up on Thingiverse too.
Yes, someone will put these up on Thingiverse. I have a bunch of things on georgehart.com. I never have enough time to post everything, but if you email me enough, that'll prod me into putting them online. I'm not averse to it, I'm just kind of swamped in many projects. So if I want to conclude, I would just need to say that this whole family of robotic devices is really, really great for getting things out of your imagination. And they've changed the world in a way that's really cool, that now really the bottleneck in making cool things is the imagination. Okay? Until a few years ago, the bottleneck was how fine are your hands or how good are your tools or whatever. But now it's what can you think of, because anything you can think of, you can figure out a way cost-effectively to get out there. And there's lots and lots more examples. Go to my website, georgehart.com, to see lots of other sculptures and 3D printed things, and to learn more about the Museum of Mathematics and all our cool things that we'll have there, and different ways that you can help us and support us. Go to momath.org. I'm happy to take questions.
Well, first let's give him a round of applause. I've got one question over here.
So were you able to figure out why it worked with the 12 sticks and not the 6 sticks?
Yes, so the question is, do I know why the 12 stick works and why the 6 sticks didn't? And it's basically because when I build these things, I know that they will fit together, but I don't know how well they lock until I actually have it in my hand. So I have to just use some intuition. And I think if I twist each of these pieces in place a few more degrees, it will work. I have to do a number of prototypes, and that's just what's so great about these robotic devices. I can make those prototypes, over the weekend, and eventually get this to the point that it does work without having to make, expensive molds or whatever you would do if this was supposed to be, say, an injection molded plastic piece. I have there's basically one parameter in this, which is a mounted twist. These are the 6 edges of a tetrahedron, each rotated about its center, the same amount as seen from outside. And I can tweak, I have sort of a slider in my own software that allows me to slide that. And I pick the spot where I think it's going to work. I have to just slide it a little bit more over. And there's a very fine line with something that's snatched together between when it just easily falls apart and when it's so tight that you can't ever get it together. And I have to experiment a bit. I'm close to that line, but I'm not quite there. Yes?
What do you think of OpenSCAD for this sort of, to be part of it, the open source parameterized modeling software?
Yeah, I've used OpenSCAD for lots of things. I mean, it's if you're a programmer type person who's used to a textural way of describing objects, it's a wonderful piece of code. Other people that work
this sort of thing.
Yeah, I mean, it's great for that. So if you can describe the coordinates, where the cylinder starts and ends, or how much you have to rotate it about each axis in a textural way, it's great. If you're the kind of person that wants to see it on the screen and move a mouse, then you probably want more of a GUI type interface. There's just different tools depending on how you work. Yes?
Are you using Mathematica to generate those designs?
I do use Mathematica. I use Java or C. I have a background. Until about 3 or 4 months ago, I was a computer science professor at Stony Brook University. So I have a long background in computer languages.
Can Mathematica export STL?
Mathematica exports STL, yeah, very well, very easily, including the special version that you need for the color for Z-Corp machines. Any programming language can do it. I mean, you can export, you can write your own STL export in any program language.
Right, but Mathematica already has.
Mathematica has built in many thousands of file conversions. It's an expensive program, but it's really fast for certain things because it has so much built in. I'm sorry?
A cheap home edition.
Yes, now there is a home edition. Yes. Mm-hmm.
Where is the Mathematics Museum in Manhattan going to be?
Right now we have a temporary office where our staff is working near Penn Station. We're very close to signing a lease for a space near Madison Square Park, right overlooking Madison Square Park, 26th, just east of 5th Avenue. We're waiting for the lawyers to finish the last little bits on that, but we're hoping that lease will be signed within a month, and then we'll be sort of gung-ho working with the architects in terms of actually renovating that space. Am I out of time?
You're out of time.
Okay, thank you.
If you ever have a time where you do not have any appointments for like the rest of the day, go to George's site and just lock in.